Okay, welcome back, statics students. This is the last recorded lecture for our winter quarter 2020. This is Bellingham Technical College ENGR 214 ampersand statics. So this is just a little addendum to our discussions about integration for finding, centroids and center of mass. In our previous lecture and a lot of the examples you'll see, all of the functions are what we would call invertible. So if you're integrating to get your x or your y centroid, what you would typically do is just invert the function and then integrate with whichever version matches your x or your y. So you would define your dA or your dV in terms of whatever your variable was that actually represented the x, y, or z centroid. This isn't always possible. And in some cases you're looking for the difference between two functions, like maybe looking at the centroid of a gap, a space between two other things. So I wanted to review a very, very handy way of calculating, in this case, the y centroid, when that's defined in terms of two functions that you can't just invert and integrate the simple way. So let's set this up, and again, thinking about our the space that we're concerned with and finding the centroid of as maybe being a gap. So if you look at your function f of x as this upper line, maybe this is defining the lower portion of some big part, and we're looking at that bottom surface or bottom edge. And likewise, the function g, which is a function of x, is this lower line here, and maybe it's defining the top surface of something. So we're interested in finding the y centroid between x equals 1 and x equal 2, over this particular area. We're looking at the y centroid of the volume that basically, or the area, that is defined by the difference between f of x and g of x. So between the bottom here and the top here, that gap and its area between this left-hand limit and this right-hand limit. So if you were going to get the x centroid, that's pretty easy. You would just take this whole area times the x centroid, integrate over x dA between x1 and x2, and dA would be in this case equal to maybe the height of what we define as this strip, and that height's pretty easy. It's just f of x minus g of x dx. So you just integrate in both cases to get the area, and then x times parentheses f of x minus g of x dx, and so on. So this would be your area, and then you just have an x multiplier to get this term, divide, and you have the x centroid. Pretty standard, especially if these are two functions that are easy to integrate with respect to x. Now how about y? The problem is y is a little bit harder. You'd have to be able to invert these two functions and then find something that represented the inversion of their difference. That's not so simple. So one trick that is something that you'll use if you haven't already in numerical integration is to define the characteristics of this strip that you use to find the x centroid. You could find the y centroid of this strip really easily. It effectively has negligible thickness or no thickness as we shrink a delta x down to a dx. So the midpoint of this strip, which is going to become a 1D kind of body, is just going to be 1/2 of its height, or 1/2 of f of x minus g of x at that point x. So I could easily determine the centroid of one of these vertically oriented strips. And that's kind of the key to getting get the y centroid, the y centroid, the y midpoint of these vertical strips. So that's the key to getting the y centroid of this entire area. I basically just add up the y centroid of all of these strips from x1 to x2. So let's kind of step through that mathematically and make sure we have our ducks in a row. We'll define point A as the strip centroid. So it's the centroid of a strip that has its own dA. So the strip area is h times its width, dx, and strip centroid's a. So strip area, strip centroid. So we can say the y-coordinate of point A for any strip is f of x plus g of x times 1/2. So the average of the difference between the two functions, or the average of the difference, the average of them put together. So it is a true average of the two function values. And then we're going to sum that y-coordinate of point A for all the strips. So we'll define, and we're going to sum it by area. So we're going to get what's effectively an area average of the y-coordinate of point A for every one of these strips. So we can define that as the integral over any dA, any point A or any y-coordinate of the strip centroid times the area of the centroid added up over all the strips from x1 to x2. So we're basically just doing a rolling average, a cumulative average between x1 and x2, not a rolling, a cumulative. So we can identify the parts here. The 1/2 f of x plus gx is effectively our strip centroid. So this is the strip centroid. dA we've already defined as h times dx, and h is f of x minus g of x dx. We're going to integrate from this x limit to this x limit. Notice that with the exception of the function values themselves, everything is now in terms of x. So we can say that the total, the area times the y centroid is the integral from our left hand to right hand x limits times 1/2 f of x plus g of x times f of x minus g of x. So that would multiply out to f squared of x plus g squared of x parentheses dx 1/2. So if you use this concept, this will get you around a case if you ever have to where you don't have an invertible function and you need to find the y centroid or the z centroid for something where you simply can't just write y as a function of x or z as a function of x. So, and this is again related to average values and will be something that you'll see again in numerical integration. So that is it. This is definitively our last recorded lecture and our last subtopic for statics, Winter 2020, Bellingham Technical College. Good luck to everyone preparing for your final exam and your further studies in materials and mechanical engineering studies.